Okay, in the last lecture, I looked at very simple structures which had a monoatomic basis and determined the value of the structure factor, showing that which HKL planes will produce reflection and for which HKL planes there would be extinction, even though the Bragg's law is satisfied. Now, in this lecture, I will consider somewhat more complicated structures which have multi-atomic bases. So, you take crystals, so I have now more than one atom present in the basis, and they could also be different atoms. But first consider an example. Let me call that as example 1, the structure of diamond. Now, in an earlier lecture, I had explained what was the structure of diamond. Well, the diamond crystal is a face centered cubic unit cell, and to that unit cell I add 2 atom bases, 2 carbon atoms at 0, 0, 0 and 1/4, 1/4, 1/4. Now, clearly, if face centered cubic has 4 lattice points per unit cell, I have a 2 atom basis. So, the number of carbon atoms would be 8 per unit cell, 4 coming from the corners and the face centers and 4 coming from atoms which are lying on 4 body diagonals. Now, what are their atomic positions now? So, position vectors we have to. So, I will have essentially 8 position vectors, and one can put this position vectors in a very simple way. First, let me write down the FCC lattice translations. So, face centered cubic lattice translations are 0, 0, 0. I have half, half, 0. Third one, I have half, 0, half, and I have 0, half and half. So, these are the 4 lattice points that are present in the unit cell. The other lattice points, as I had explained even in the earlier lecture, belong to another unit cell. Add to this the 2 carbon atom vectors. So, I am adding the motif to these translations. So, these are the lattice translations. And add to this the position coordinates of the 2 carbon atoms, and which are 0, 0, 0 and 1/4, 1/4, 1/4. So, I add 0, 0, 0 to all the lattice point coordinates, and that will give me the position of the 4 carbon atoms. I add 1/4, 1/4, 1/4 again to the lattice translation coordinates, that will give me the 4 carbon atoms which would be lying on the body diagonals. So, now instead of adding all of these, I can write my structure factor in a rather simpler way. So, my structure factor, let me just rewrite that equation. So, in this case, of course, this would be M would be 8 atoms. So, there will be 8 terms in the structure factor. But as I said, let me not write all the 8 terms directly, but let me break this structure factor into 2 terms. The structure factor, I want to break it up into the motif or the basis part and the lattice part. And then it can be written as, now since all the atoms are carbon atoms, so all of them have the same atomic scattering factor. Therefore, I can take the atomic scattering factor Fj outside the summation and let me just call it as F, representing the atomic scattering factor for the carbon atom. First write the motif part. So, e to power I 2 pi and the first coordinate of the first carbon atom at 0 0 0. So, I substitute in this and I will get a 0 plus e to power I pi, or rather I e to power I 2 pi h by 4 plus k by 4 plus L by 4 multiplied by, now I take the lattice part essentially. So, I will my first, since 0 0 0 half half 0 half 0 half 0 half half, I already know that what is going to be for this, the first term would be 1, second term would be e to power I pi h plus k plus e to power I pi h plus L plus e to power I pi k plus L. So, now looking at this expression, suppose I were to multiply the two terms, this representing the motif and this representing the lattice. If I multiply the two terms, you can very clearly see that I am going to end up with 8 terms. So, it is essentially just by breaking it into 2, things become a little simpler. Now, for the lattice part, I already know from the previous lecture that when would this lattice term will go to 0, when it will not be 0. So, very clearly this term would be 0 when HKL mixed, and it is going to be 4 when HKL unmixed. Now, if HKL are mixed, there is extinction, I do not need to do any other analysis. So, let us consider the situation when HKL are unmixed. If HKL is unmixed, the lattice term will give me a factor of 4. So, this will become 4F, and now looking at the motif term, the first term in this is e to power I 2 pi into 0. So, that will give me 1, and the second one would be e to power I pi h plus k plus L divided by 2. Now, can the structure factor still go to 0? Yes, it can if this term is minus 1. Now, when can this term be minus 1? So, consider if h plus k plus L divided by 2 is an odd number. Another way of putting it is when h plus k plus L is a odd multiple of 2. If that is the case, then I will have e to power I pi h plus k plus L becoming minus 1. So, this implies e to power I pi h plus k plus L by 2 going to minus 1, which implies that f is equal to 0 and you get extinction. So, this extinction is over and above what extinctions you will get for this being a face centered unit cell. So, this is an extra extinction. Now, if I have h plus k plus L upon 2 being an even number, then this implies that e to power I pi h plus k plus L upon 2 is equal to plus 1, and hence f would be 8f, because 1 plus e to power I pi h plus k plus L upon 2 would be 2. So, 2 times 4 8. So, I get 8, or f star is going to be 64 f square. So, in the unmixed case, I have specifically seen a situation, this specific situation, where necessarily h, k and L are all even. But you also have a situation when h, k and L are all odd. Now, in that case, h plus k plus L upon 2 would be a fraction, and I leave this to you to solve what would be the value of f star in the case when h, k and L are all odd. Now, let me take another, or let me kind of generalize what I have done here. In general, we can break the structure factor into two components. As I had said, motif and a lattice. So, let us say that my lattice coordinates, so lattice point coordinates in the unit cell are given by uj, vj, wj, where j goes from 1 to m. So, if it is a primitive unit cell, then there will be only one lattice point. If it is a body centered cell or an end centered cell, there will be 2 lattice points, and if it is a face centered cell, it is going to be 4 lattice points. So, m will be 1, 2, or it could be 4. The motif could have very large number of atoms in many cases, and let me call the coordinates of the motif atoms for the jth atom. So, for the jth atom, or let us I have used already j, let me say for the pth atom, the coordinates are xp, yp, zp. So, these are going to be fractional coordinates in the crystal space, and similarly their atomic scattering factor correspondingly for individual atoms can be, so for the pth atom Fp. So, then I can write the structure factor equation in a rather simple manner. One can write in the following way. Let us say that there are how many atoms in the motif? Let me say that there are now n atoms in motif. They can all be same, or they can all be different, or some different, some same. It can be any combination. So, I can write the structure factor now as 2 summations p equal to 1 to n. This is the motif part I am writing. Atomic scattering factor Fp e to power I 2 pi h xp plus k yp plus L zp multiplied by another summation term, which is the lattice part, which is j equal to 1 to m, and there will be atomic scattering factor will be part of the motif, and here only I have the lattice point. So, I will simply have e to power I 2 pi multiplied by h u j plus k v j plus L w j. So, I can write the structure factor in this form. Now, this expression could be quite useful when you have a large number of atoms in the motif and you want to analyze what will be the structure factor. So, if I take this equation and if I had used it in this, I essentially it is the same in the case of diamond, it is exactly the same. Now, let us take an example. So, let us say I am now going to take example 2, and this example I am going to take is of a NaCl crystal, which is again face centered cubic plus motif, let us say chlorine ion at 0 0 0 and sodium ion at half half half. Now, I want to calculate the structure factor for this. So, chlorine ions are at the corners, face centers, sodium ions is at the body centered position and also at the center of all the edges. So, the structure factor now can be written, first I write the motif part. Now, there are basically 2 atoms in the motif. So, n is equal to 2, FCC my m is equal to 4. So, I have 2 terms in the first. So, the first term, so I have now 2 different atoms as well. So, for let us say the first term is going to be my chlorine atom. So, I will call that as F subscript chlorine. So, this is the atomic scattering factor for chlorine, and I substitute 0 0 0 out here. So, that will give me 1. So, F chlorine will be the first term in the motif part. The second one now is a sodium atom. So, F Na, and I substitute half 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 out here. This gives me e to power I pi h plus k plus L. Now, I write the lattice part we are already now familiar with. It is the face centered unit cell coordinates, and that would simply give me 1 plus e to power I pi h plus k plus e to power I pi h plus L plus e to power I pi k plus L. Now, this I already know that this becomes 0 for HKL mixed, and this is equal to 4 for HKL unmixed. So, I need to just look for analyze this for HKL unmixed, because when HKL are mixed anyway the structure factor goes to 0, I do not need to analyze anything else. So, therefore, F the structure factor for HKL unmixed becomes FCl plus FNA e to power I pi h plus k plus L. Now, this is very simple to analyze. Whenever h plus k plus L is even, this exponential term will go to plus 1. Whenever h plus k plus L is odd, the exponential term will go to minus 1. Hence, I can write that F equals 4 times FCl plus FNA for h plus k plus L equals even, and the structure factor F will go to 4 times FCl minus Fna for H plus K plus L taking up an odd number, and F star would give me the intensity. Now, let me take one last example before I conclude the lecture. Let me consider a titanium crystal. Now, this titanium crystal can have a crystal structure which is called as the hexagonal close packed. Now, remember, there is no such lattice as hexagonal close packed, but it is referred to the hexagonal close packed because that is the most densest way of packing spheres in a hexagonal unit cell. So, really the crystal structure itself, so the crystal is a primitive or simple hexagonal unit cell with two titanium atoms. So, this is again I have more than one atom in the basis, but my unit cell is primitive, and these two titanium atoms are located at 0, 0, 0 and 1/3, 2/3, half. So, the structure factor F, now I can write, I write the motive part first. Now, again the atomic scattering factor is the same because same kind of atoms are present. So, we can just call it as FTI perhaps, multiplied by motive will have two terms because there are two atoms in the unit cell. So, n is equal to 2. In this primitive, the lattice points are m equals 1. So, FTI is taken out of the summation, and I can write FTI multiplied by 1 plus e to power I 2 pi h plus 2k divided by 3 plus L by 2. The lattice part, I have only one lattice point per unit cell, it is at 0, 0, 0. So, the lattice part is simply unity 1, we have already seen. For the primitive lattice, there will be no extension. So, therefore, let me kind of simplify this a bit. Let me take a parameter called Q, and let me write it as 2 times h plus 2k divided by 3 plus L. So, I have taken this factor of 2 in the exponential inside the brackets. So, I can write the structure factor as FTI 1 plus e to power I pi q. Now, clearly f would go to 0 if e to power I pi q becomes minus 1, which implies that f will be 0 when the value of q is an odd number. But otherwise q here can be a fraction as well, and then this remains in complex form. So, the best way to solve this is to not solve it at this stage, but let us find out the intensity being proportional to f star, the product of the structure factor and its complex conjugate. So, let me write down this product. So, first I write down FTI 1 plus e to power I pi q multiplied by, now I write down the complex conjugate part of it. So, again FTI multiplied by 1 plus e to power minus I pi q, and then we now expand this. So, it will become F Ti square times, if I multiply the two bracketed terms, I will get 2 plus e to power I pi q plus e to power minus I pi q. Now, recall from the previous lecture that e to power I x plus e to power minus I x is equal to 2 cos x. Therefore, I can write now f f star to be f T I square, this goes to 2 cos x. So, the factor of 2 can be taken out, put here, and I will get 1 plus cos of pi q. So, we have in this process gotten rid of the complex terms, and one is now we can analyze this. So, in order to analyze this, so f star would be 0 for cos of pi q becomes minus 1, and this can happen when q is an odd number. So, cos pi, cos 3 pi, cos 5 pi, they will all have a value of minus 1, while if q is even, then you have cos 2 pi, cos 0, cos 2 pi, cos 4 pi, that would be plus 1. So, let us see how can q be an odd number. So, let me write down first what is q. So, q is equal to 2 times h plus 2k by 3 plus L. So, let us say if h plus 2k upon 3 is a multiple of 3, 3 times n is some integer. So, whenever h plus 2k upon 3 is a multiple of 3, which means that the first term which has a factor of 2, this will be even. So, it will be an even number, and then if L is odd, then even plus an odd number becomes an odd number. So, q will become odd. So, let us examine the situation. H plus 2k is a multiple of 3, and let us say L equals odd. This implies that q is odd, and this implies that from above f star will be 0, and one will get extinction. What happens if L is even? If L is even, then in that case q will be also even. So, cos of pi q will be plus 1. So, this gives me cos of pi q would be plus 1. Hence, f star, which is this. So, bracketed term will give me a plus 2. So, f star would be 4 times f T I square. Now, what other possible values? So, the other possible values is one should see this first this term. Since h and k are integers, h plus 2k can take up being a multiple of 3, or it can take up a multiple of 3 either plus or minus 1. Now, for example, let me just take this when it is a multiple of 3, which you have already done. So, if I have, let us say, an example of one example for a reflecting plane, in this case can be 1 1 1. Now, in this case h plus 2k is 3. So, it is a multiple of 3, hence f star will be 0. suppose I had, if I had, let us say, and here I can take an example of 1 1 2. In this case, h plus 2k is a multiple of 3, but L is even. Then I get this. Now here, so 3n is taken care of, 3n plus minus 1. So imagine I have, let us say, 1 to L as my HKL plane. So this implies that h plus 2k, h plus 2k would be 5, which I can write it as 3n minus 1, where n is equal to 2. So just an example I have given. So we will now consider the case when h plus 2k is three n plus minus 1. If I take this, then what would be q? So q will be equal to, substitute in this, I can write this as 2 times 3n plus minus 1 divided by 3 plus L, and hence q I can write it as, let us expand this a bit. So I can write it as 2n plus L plus or minus 2 by 3. So this implies that cos of pi q becomes cos of 2n plus L pi plus or minus 2 pi by 3. So you can see here that 2 pi by 3 is simply 120 degrees, and 2n plus 1 can be either odd or even. So if I take 2n plus L as odd, then I know that cos pi q is a, here I have inside this cos term, I have an odd value, odd times pi, and this would simply give me minus cos 2 pi by 3. So I have cos of 2 pi by 3. Now what is minus cos 2 pi by 3? Cos of 2 pi by 3 is minus half, there is a minus outside, so therefore this would be plus half. So cos pi q is half, put it in this equation, and this would give me f star to be equal to 3 f t I square. Now when would 2n plus L be odd? 2n plus L will be odd when 2n is always even. So 2n plus L can be odd only if L is odd. So the key here is that for the situation when h plus 2k is 3n plus or minus 1, if L is odd, then my structure factor would be given by 3 f t I square. So it is non-zero, so no extinction, but it will have a different intensity as compared to the situation when h plus 2k upon 3 is an even multiple of 3. Actually this I have made a small mistake, h plus 2k is an even multiple of 3. When h plus 2k is an even multiple of 3, then I will get this to be an even number, h plus 2k upon 3 into 2. Now consider when L is even here, then what happens to 2n plus L? Well, 2n is always even, so L is even, so this is even. This implies that cos of pi q is simply cos of 2 pi by 3 coming from out here, and this gives me minus half, and hence I substitute this cos pi q as minus half in this equation, and I will get f star as simply f T I square. So, this way I have considered all possibilities for this titanium crystal or any other crystal which has a structure of a primitive hexagonal unit cell with 2 like atoms packed in such a way that we form a hexagonal close packed structure. Thank you.